Hello everyone. The title of this video is Divide Roots. So every exercise I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and it's their Intermediate Algebra 2nd edition text. And I'll be working on the even numbered exercises under the heading Divides Square Roots, which is kind of a misnomer. That's why I changed it to just Divide Roots, because you notice even in number 246 part B, you're dividing cube roots. Right? There are square roots and cube roots being divided throughout this heading, this section of exercises. Alright, so I'll be working on the even numbered problems, because if you notice, the odd numbered problems have a link to them where you can click on and go see the solutions yourself. So I'm just going to do the questions that don't have solutions in the book, and I will be having time. I will be putting timestamps in the description of this video. So you can click around and jump from example to example. Example 1 will correspond to exercise 246. Example 2 will correspond to 248, and so on, 250, 252, all the way down to number 258. Alright, and one other request I make of you is that when I bring up a new question, pause the video and try to work on that question, that example yourself before you watch me do it. Right? Because if you're just watching me do these things and not practicing yourself, chances are you're not learning all that much. Alright, so let me bring up number 246, which again I'm calling example 1. Right, again, and I've written the exercise numbers underneath the example numbers on my paper. And we're asked to simplify, right? Divide and simplify. And every exercise in this video is going to make heavy use of the quotient property for radicals. I'll write that off to the side here just to refresh our memory. So the quotient property was, if I have the nth root of a fraction, we can split it up and take the nth root of the numerator divided by the nth root of the denominator, and vice versa. Right? If you see a quotient of two roots, two of the same kind of root, right, dividing two nth roots, you can put it together as a single nth root of a fraction. Right? But the only way this worked out, right, the only way this property applied is if these nth roots were real numbers. Right? As long as the nth root of A and the nth root of B are real numbers. Okay. So we only have to worry about this, can I use the quotient property or not, when we're talking about even roots. Right? Remember, for even roots, the radicand needs to be non-negative in order for the expression to be a real number. Right? If you're taking the even root of a negative number, that's not real, and this property doesn't apply. Now for odd roots, cube roots, fifth roots, etc., the property always holds, because odd roots of positive numbers, odd roots of negative numbers, those are all real. Okay, don't worry about imaginaries with odd roots. Alright, so here in part A, I have even roots, right? Square roots being divided. And the radicands are both non-negative. They're positive 48, positive 75. So these are real numbers. So I can apply this quotient property. And that's what I'll do for the most part for most of these. Is I'm going to basically be jumping back and forth a lot between the left and right side of this property. So using the quotient property, we can say this is equivalent to the square root of 48/75. Right. And then I'm going to simplify this fraction. Right. Now 48 is 3 times 16. 75 is 3 times 25. So if you divide by 3, both the numerator and denominator here or cancel out the common factor of 3, this is just the square root of 16/25. Alright, which you could apply the quotient property again if you wanted. Take the square root of the numerator is 4, right, and the square root of the denominator is 5. So this ends up being 4/5, right? 4/5. Now, I'm going to check my answer as well. Alright, now I'm going to do this with a calculator. I have a TI-84 emulator, TI-84 Plus, that I'm going to pull up here. And what I'm going to do to check my result is I'm going to enter the original expression, right, the expression we were given in the beginning, and then I'll enter the final expression. Well, I know that the final expression is 0.8. So if I enter this first expression and end up with 0.8, well, that's the same as 4/5, and I'll know that I did everything correctly. Alright, so let's do that. So we have this original expression was the square root of 48 divided by the square root of 75. And you see 0.8, which is, as I mentioned, 4/5, right? 0.8. So this is correct, right? What I have here, 4/5 is in the same as the original expression and a totally simplified fraction. Wonderful. All right, so let me clear this and get that out of here. Alright, and I'm doing the same thing the rest of the time. Basically, again, just jumping back and forth from side to side here with this quotient property. Again, the only way this applies is if the roots are, real numbers. So keep that in mind. Alright, now also pay attention to what kind of roots are being taken. Right, in part B, they're cube roots. Right, cube roots. Alright, so just like before, I got the cube root divided by the cube root. These are both real numbers, so I can apply the quotient property. Say this is equivalent to the cube root of 81/24. And once again, both these 81 and 24 have a common factor of 3. 81 is 3 times 27. 24 is 3 times 8. So when I cancel out the common factor of 3, we have the cube root of 27/8. Right, 27/8. And then I could apply the quotient property again, say the cube root of 27, the numerator, that's just 3, right? 3 cubed is 27. And the cube root of 8, the denominator is just 2, right? 2 to the third is 8. So the final result here is 3/2. Right? And once again, I'll pull up a calculator and we'll check this. So pull my calculator up here. Again, I'll punch in the original expression, which was the cube root, and you better know, hopefully you know on whatever calculator you're using how to enter different roots, right? Cube roots, fourth roots, and so on. So it was the cube root of 81, and then that divided by the cube root of 24. And if I get 1.5, I'll know I did a good thing. All right, 1.5, because that's 3 halves. Right? 3 divided by 2 is 1.5. Great. So that's it for that question. Like I said, every question is going to be very similar to this. You know, some might have variables though, and when the expression has variables, one other thing I like doing, and you should do as well, is, you know, state the domain of that variable. You know, state what values are allowed to be plugged in for that variable. Right. So next question, right, example 2, which is exercise 248 in the text. So you see, like I said, there are now expressions with variables. So before I do anything, I'm going to state off to the side, or maybe just underneath here, some, you know, what's the domain of this expression? What are the values I can use for n here? Now these are even roots. Remember, even roots, the radicand can't be negative. So 108 times n to the 7th, I don't want that to be negative. Well, that would be negative if n were negative, right? A negative number to the 7th power would be negative. So n needs to be greater than 0, right? N needs to be positive in order for us to actually still be dealing with real numbers here. Now notice I said n has to be greater than 0, but not equal to 0. Now the reason for that is the denominator, right? If n were equal to 0, you'd have the square root of 0. You'd have 0 in the denominator, and hopefully you recall that you can't have those, right? You can't have zeros in denominators. Dividing by 0 is undefined. So just keep this in mind, right, that n has to be positive in order for us to keep going with this problem, in order for us to be dealing with real numbers. Alright, so if n were positive, like we're assuming, then we can actually use the quotient property. This will be equivalent to the square root of, 108 n to the 7th over 243 n to the 3rd. Alright, and we'll simplify this fraction. So we're looking for common factors. I'll tell you right now, 108 and 243 have 9 as a common factor. This is 9 times 12. And this is 9 times 27. So that would reduce to 12/27ths, but that reduces even further to 4/9ths. Alright, so in fact they had 27 in common. This is 27 times 4, this is 27 times 9. So 4/9ths, and then n to the 7th divided by n cubed would be n to the 4th in the numerator. Right, because 3 would cancel, 3 of the n factors would cancel, and you'd be left with n to the 4th in the numerator. Great. And now I can, again, since n is positive here, these are going to be, each of these square roots is real. The square root of 4n to the 4th would be 2n squared. And the square root of 9 is 3. Right? There you go. Right, notice I didn't need to use absolute value symbols here, right? Normally, when you're simplifying an even radical, square root, 4th root, 6th root, right? Remember, very often we needed absolute value symbols, because when you see an even root symbol, your final result should be the positive root, right? The non-negative one. But here we have n squared, which will always be positive, non-negative, whatever, so I don't need absolute values. Additionally, we said at the beginning that n has to be a positive number, so that negates the need for absolute value symbols. But you got to keep that stuff in mind. Now, if you wish to check this, right, just replace n with any positive number and see if the value of the original expression is the same as the value of the final expression. So for example, right, I'll do this. This will be the last one I use the calculator to check. Right, I'll leave the rest to you. For example, if I let n be 1, that'd be easy. Both of these should have a value of 2/3, right? If n were 1, this would be 2/3 at the end, and this should be equal to 2/3 in the beginning. Let me pull the calculator back up. Alright, let me replace n with 1. So this should just be the square root of 108 divided by the square root of 243. Alright, so let me punch that in. Square root of 108 divided by the square root of 243. And hopefully you get 0.666666667. You know, it's going to give you a 7 eventually because it's a calculator. It stops at some point. But that's 2/3, right? Right. This last expression, 2n squared over 3, if I replace n with 1 there as well, you'd end up with 2/3, which is the same. And you could do the same again for any positive value of n. Replace n with any positive value, punch it in here, punch it in here, punch it in the last expression, and you'll see that you get the same result, the same number every single time. Okay? Not always 2/3, right? If I replaced n with 2, this would end up being 8/3, and that would be 8/3, right? But just know that the original expression and final one will end up being equivalent. Okay. Now, part B, pardon me. Now these are odd roots, right? Odd roots, so the variables can be any number as long as the denominator is not 0. So once again, off to the side here, just going to write that y can't be 0, because if y were 0, you'd have a denominator of 0. But other than that, you're fine. Y can be a positive number, y can be a negative number, and these will be real. Right? And since they're both real, I can apply that quotient property, right? This is the cube root of 54y divided by 16y to the 4th. And let's simplify this fraction. Now 54 is 2 times 27, 16 is 2 times 8. You cancel the 2's, and you got the cube root of 27 over 8. Right, that's 54/16 reduced. And then y over y to the 4th, you'd end up with y to the 3rd in the denominator, right? One of the y's would cancel. All right, then I can split it up again. Cube root of the numerator, cube root of 27 is 3, right? And the cube root of 8y cubed would be 2y. All right, so 3 divided by 2y is our final result here. All right, wonderful. And once again, you can test this out. Replace y with any number that's not 0, with 1, with -1, 2, 2.5, -5.4, whatever you want. And the value of the original expression should be equal to the value of this final expression. But I leave it to you to check now from here on out. Wonderful. All right, next question. All right, number 3, which corresponds to number 250 in the text. So part A is square roots yet again. Now, in order to be able to use the quotient property, these radicands need to be non-negative, right? And the only way that's happening is if q is a positive number. Alright, so we're going to be saying, the only values I can actually plug in for q here are positive numbers. Right, so that way I'm dealing with reals. Alright, so if q is positive, and notice I said just positive, not 0, because if q were 0, the denominator would be 0, and that's bad. So now I can put them together with the quotient property. And you know what? I see something nice here. Let me just do this. So 196q over 484 q to the 5th. And I know what the square root of 196 is. 196 is actually a perfect square, and so is 484. So I'm just going to do this. All right. Now, if you want to reduce that, fine. There's nothing wrong with that, but I'm just going to cancel the q's. So we have 196 in the numerator and q over q to the 5th. That would leave me with q to the 4th. One of the q's would cancel in the denominator, and 484. The square root of 196 is 14. Right? 196 is actually 14 squared. And the square root of 484 is 22. Right, so this is 22. And then the square root of q to the 4th would be q squared. Right? And we can simplify at the end. You can simplify early, you can simplify late, as long as you end up simplifying the fraction, right? 14 and 22 have 2 in common. You cancel those out, you end up with 7. 7 divided by 11. Right? So 7 in the numerator and then 11q squared in the denominator. Now, like I said, you could have just, you could have simplified earlier. This is 4 times 49. This is 4 times 121, so you'd end up with 49 over 121, and then take the square root, so you get 7 over 11. Alright, but either way is fine, and there you go. Alright, and again, you can check it out, test it, plug in any positive number for q, and see that the value of the original expression is the same as the value of the final expression. But I leave that to you. Alright, part B. Cube roots. Again, the only value that the variable can't be is 0, because that will make you divide by 0. So m can't be 0, but it can be anything else, right? M can be a positive number, it can be replaced by a negative number, and you're fine. Alright, so once again, as long as m is not 0, these will be real numbers. We can apply the quotient property. The cube root of 16m to the 4th divided by 54m. And these both have a common factor of 2. Actually, they have a common factor of 2m. Right, so this is the cube root of 8m cubed divided by 27. Right. When I cancel out the common factor of 2m. And then the cube root of 8m cubed would just be 2m. And the cube root of 27 is 3. Right? So 2 times m divided by 3. Right? Wonderful. And once again, I leave it to you to check out. Replace m with any non-zero number, positive or negative, and see that the value of the original expression is going to be the same as the value of this expression at the end, 2m over 3. Great. Next question. Number 4, which corresponds to number 252 in the text. Alright, so this has 2 variables in it, r and s. But once again, I'm going to write off the restrictions. These are even roots. Even roots. So the radicands can't be negative if we're talking about dealing with real numbers and using the quotient property. Now notice that s is raised to an even power in both these radicands, s to the 10th, s to the 4th. So s can be any number I want. As you raise it to an even power, it's going to be non-negative. It's r, right, that has an odd power in one of these, actually both of them. So r can't be negative, right? R has to be positive. Notice I said r has to be greater than 0, but not equal to 0, because if r were equal to 0, you'd be dividing by 0. The denominator of this whole thing would be 0, and that's bad. So r has to be positive, and s can be anything I want except 0. S can't be 0. Alright, so when it comes to s can be positive, s can be negative. And I'm taking an even root. Remember the even root symbol, any even root symbol, the final result has to be the positive root. That symbol is asking you for the positive root. So I may need to use absolute values here. Alright, and you'll see what I mean in a second. Alright, so now with these restrictions, with r positive and s non-zero, these are going to be real numbers. I can apply the quotient property. Alright, then we'll simplify the fraction. So we have the square root. Now 98 divided by 2 is simply 49. R divided by r cubed, the r would cancel with one of these. You'd have r squared in the denominator. And s to the 10th divided by s to the 4th, you'd have s to the 6th in the numerator. Alright. Now, square root of 49 is 7. Square root of s to the 6th would be s to the 3rd, but. Remember, s can be any number but 0. So if s were negative, this would be a bad response. So I need this to be non-negative, right? Remember, this symbol is asking you for the non-negative result. So I need to throw absolute value symbols around that. Alright, this is 7 times the absolute value of s cubed. Because, again, s can be a negative number in this expression. But I want my final result to be non-negative. Divided by, and then the square root of r squared is r. Now remember, normally we would put absolute value of r, but r was a positive number. R has to be positive. So there's no need for absolute values here. I hope that makes sense. Right. And there we go. 7 times the absolute value of s cubed divided by r. Now, very often, and I don't understand why certain textbooks do this, but because I think you should have to remember when to use absolute values and when not. But very often, you'll be asked to simplify radicals and all that and not worry about the absolute value symbols for some reason. So if we were to assume, big if s was assumed to be positive, right, if they tell, you'll see this in a lot of books where they'll tell you, assume that all the variables represent positive numbers or non-negative numbers. If that's the case, they're only doing that so that you don't have to write the absolute value symbols. It would just be simplified to 7 times s cubed divided by r, right? So I mean, most instructors would take this. Not me though, alright? The true proper result would be 7 times the absolute value of s cubed divided by r. But just in case you have an instructor that doesn't mind ignoring the rules, this would be fine. Because if you look back too, right, if you look back at the instructions from the textbook, it says just in the following exercises simplify, and nowhere does it say assume the variables are positive. Doesn't say that anywhere. So you should have to use absolute value symbols in certain scenarios. I just want to throw that warning out at you. Okay. So number 4, part B. Well, now we have cube roots, right? Odd roots are fine. You can take odd roots of anything, any number, and it's still going to be real. I just want to make sure that we don't ever divide by 0 or have 0 to a negative power, because that's the same thing as dividing by 0 if you remember how negative powers work. So y can't be 0 and z can't be 0. Those are my only restrictions, right? Y can't be 0, z can't be 0, and yeah, those are the only restrictions on the variable here. It can be anything else. Y can be positive or negative, z can be positive or negative. Alright, so again, as long as y is not 0 and z is not 0, we have, dividing real numbers here. I can apply the quotient property. So negative 375, y to the 4th, z to the negative 2nd, divided by, and then 3 times y to the negative 2nd, z to the 4th. And then let's simplify this. Right? This is the cube root. Now, negative 375 divided by 3 would be negative 125. Y to the 4th divided by y to the negative 2nd would be y to the 6th, right, in the numerator. Now, you could also do that by multiplying the numerator and denominator by y squared. That'll give you y to the 6th, and then y to the 0. And remember, anything to the 0 power is 1, so that would be gone. And then same thing for the z to the negative 2nd over z to the 4th. If you multiply the numerator and denominator by z squared, that'll be z to the 0 divided by z to the 6th. So you have z to the 6th in the denominator, right? And z to the 0 would just be 1. Okay, so I'm getting this nice perfect, these are all nice perfect cubes. Right, the cube root of the numerator. Cube root of negative 125 is negative 5. Right, so it's negative 5, and then the cube root of y to the 6 would be y squared, divided by, and then the cube root of z to the 6th would be z squared, right? Z squared to the 3rd would be z to the 6th. And there we go. Negative 5 times y squared divided by z squared is our final result. And again, if you'd like to check this out, test it out, replace y with some non-zero number, replace z with some other non-zero number, and plug them in. And see that you'll see that the value of the original expression is going to indeed be the value of the final one. All right. Great. All right, so let's do that again. Number 5, which corresponds to exercise 254. Part A. Alright, so once again we have even roots. Alright, even roots. Now obviously C and D can't be 0. But also notice that the C's and D's in these factors are raised to odd powers. So they can't be negative either, right? Because if C were negative or D were negative, you'd be taking square roots of negatives which aren't real. So here, C has to be a positive number, and D has to be a positive number as well. Now, because I said this, right, because we note that C has to be positive and D has to be positive in this initial expression, I won't need absolute value symbols later, because the variables are already known to be positive numbers, or they have to be positive. I hope that makes sense. Alright, so I'm just going to simplify right away here. This is the square root of, and then 810 divided by 1,000 would reduce to just 81 over 100. Alright, they both have a common factor of 10. And then c to the negative 3 over c to the 1, I'd multiply the top and bottom by c cubed to give me c to the 4th in the denominator and 1 in the numerator, right? C to the 0. Then d to the 7th over d to the negative 1, I'd multiply the top and bottom by d to the 1st, giving me d to the 0, or 1 in the denominator, and then d to the 8th in the numerator. Right, and all these are nice perfect squares, right? The square root of 81 d to the 8th would be 9 d to the 4th. And the square root of 100 c to the 4th would be 10 c squared. So I mean, even if I didn't say this, that c has to be positive and d has to be positive, you still wouldn't need absolute value symbols here, because c and d are both being raised to even powers at the end, and never going to be negative. And there you go, 9 times d to the 4th divided by 10 times c squared. All right, and once again, replace c with any positive number you want, and d with any positive number you want. Punch it in the original expression, punch it in the final expression, and you'll see you get the same result. All right, in part B, cube roots. So again here, the only values that the variables can't be are 0. Right? A can't be 0, and b can't be 0, but anything else is fine here. Yeah, and then I can apply the quotient property, and I'll do the simplification first, right? So 24 divided by negative 81 would be negative. Just put the negative out front here. Then 24 and 81 have a common factor of 3. That would reduce to 8/27. 8 over 27. Then a to the 7th divided by a to the negative 2. I'd multiply the top and bottom by a squared. That gives me a to the 9th in the numerator, and 1 in the denominator, a to the 0. And then b to the negative 1 over b squared. Multiply the numerator and denominator by b to the 1st. You'd have 1 in the numerator and b cubed in the denominator. Alright, so hopefully you remember this, right? The odd root of a negative is just negative. So I'll put negative sign. And then the cube root of 8, a to the 9th, would be 2a cubed in the numerator. And the cube root of 27b cubed would be 3b. And no need for absolute value symbols, right? These are odd roots. You never have to worry about that junk with odd roots. All right, so it's negative, 2a cubed over 3b. And once again, if you want to test it out, check it a little bit. Replace a with some non-zero number, replace b with some non-zero number, and plug them into the original expression, plug them into the final expression. Should give you the same value all the time. All right. Now my last page here has got 2 separate problems here. Number 6, example 6 is exercise 256 in the text. Again, dividing square roots. Now notice that a and b are both factors in this denominator here, so a can't be 0, b can't be 0. And both a and b are raised to some odd power in one of these radicals, right? Here a cubed, here a to the 1st, so a can't be negative, right? A has to be a positive number. In order to keep the 72a cubed b to the 6th a non-negative. B to the 6th, that'll always be non-negative, but a cubed won't be, right? So a has to be positive. Alright, and then if a is positive, well then down here, if a is positive, I want b cubed, that factor, to also be non-negative, also be positive. That's only going to happen when b is positive, so the restrictions here, in order to be dealing with real numbers, a has to be positive, b has to be positive in order for both of these to be real, and for us to be able to apply the quotient property. So now that if a is positive, b is positive, I can apply the quotient property. These are both real numbers. Now 72 over 3, they have a common factor of 3. And 72 divided by 3 is 24. In fact, there won't be a denominator. Right? 3 times 24 is 72. Then a cubed over a is a squared. b to the 6 over b cubed is b to the third. So I know no denominator, just the square root of 24a squared b cubed. Now finally, right, the first 5 questions, all the parts of the first 5 questions, we ended up with perfect squares for square roots and perfect cubes for cube roots, but now we're not. 24 is not a perfect square. A squared is, right, obviously its power is a multiple of 2. But b cubed is not a perfect square, right? The power is not a multiple of 2. But so we have to break this up. We have to simplify like we usually simplify radicals, right? Break it up using the product property to a square root times a square root. And I'll break it up to the square root of perfect squares. Now, 24. A perfect square that goes into 24 evenly would be 4. This is 4 times 6. Right, so square root of 4 times square root of 6, that would be square root of 24. A squared is a perfect square, so I'll put that in with the 4. And then b cubed is not, but b squared is, right? I can break up b cubed to b squared times b. Right? So I've broken up the square root of 24a squared b cubed to the square root of 4a squared b squared times the square root of 6b. And again, you can use this product property because everything's a real number, right? If a and b are positive, these are all real numbers here. So we can apply that property. Alright, then the square root of 4a squared b squared would be 2ab. Now again, I know that normally we'd put absolute value symbols around these, because these can be negative, but, remember back in the beginning we said in order for us to go through this, we're assuming that a has to be positive and b has to be positive. So if a is positive and b is positive, there's no need for absolute value symbols here, so I'm just going to write 2ab. Okay. Then times the square root of 6b. And that's as simple as that radical will get. Alright, so this ends up being equal to 2ab times the square root of 6b. And then again, if you want to check it out, you want to test it, plug in some positive value for a, plug in a positive value for b, and plug them in the first expression, plug them in the last expression, and they should give you the same value. Alright. So for example, an easy one would be if a was 1 and b was 6, both expressions would end up giving me the value of 72. And I leave it to you to check that. Okay. And then finally, this is the last question, number 7, exercise 258 in the text. Dividing cube roots, right? So I don't have to worry about having a non-negative radicand. I just don't want the denominators to be 0, right? So x can't be 0, y can't be 0 either, right? Because 0 to a negative power is undefined. Right? Alright, so x can't be 0, y can't be 0, but they can be any other number, any positive number, any negative number. Alright, so as long as x is not 0 and y is not 0, we can continue and use the quotient property. And 162 divided by 2 is 81. Then x to the negative 3 over x to the 3 would end up being x to the 6th in the denominator. Right. And then y to the 6th over y to the negative 2nd would be y to the 8th in the numerator. So I have 81 y to the 8th over x to the 6th. Now we'll break this up. I'll use the quotient property again, just going the other way. This is the cube root of 81 y to the 8th divided by the cube root of x to the 6th. Now the denominator has x to the 6th. That's a perfect cube. All right. That's going to be x squared. Right, the cube root of x to the 6th. The cube root of 81 y to the 8th, right, needs to be broken up to the cube root of 27 y to the 6th. Right, those are perfect cubes, times the cube root of 3y squared. Right, these are not perfect cubes, 3y squared. And the cube root of 27y to the 6th would be 3y squared. So 3y squared times the cube root of 3y squared in the numerator, right? So notice, again, the numerator wasn't a nice perfect cube like in questions 1 through 5. This is as simple as this radical gets. So we have 3y squared times the cube root of 3y squared in the numerator, and just x squared in the denominator. And once again, if you want to test it out, plug in any non-zero value for x, any non-zero value for y, plug them in the original expression, plug them in the final expression, and you should get the same value all the time, no matter what you plugged in for x or y, again, as long as they're not zero. And that's it. So I'm hoping that watching me go through these 7 questions here helps you in some way when you're asked to divide roots on your own. All right, thank you very much for watching.